Hi, everybody. Can everybody hear me okay? All right. My name is Marek Kolodziej. I'm a research engineer at Nitro. And today I'm going to be talking about functional programming in Scala, how they form the perfect combo for machine learning. I know I shouldn't be really advertising things, but since this is a programming conference and there are a bunch of really interesting programming conferences going on in San Francisco next month, I just wanted to mention them because they're all functionally oriented. There's FinagleCon run by Twitter. There's Scala by the Bay, Big Data Scala, focused on technologies such as Spark and Kafka. And there's also the complete pipeline training for the so-called SMAC stack, that is Spark, Mesos, Akka, Cassandra, and Kafka. And if you're interested, the organizer of the conference, Alexei Krabrov, basically wanted to offer a discount for the participants. So that's the code, and that'll be available afterwards in case you need to look at it. Meanwhile, I would like to go into the presentation itself. So the agenda for this presentation is to cover the traditional data science and machine learning tools and why, in my opinion, they're somewhat deficient, at least from a functional programmer's point of view. And then look at the JVM alternatives, but specifically the Scala alternatives, because we're talking about functional programming here. It could have been Clojure, but I just happen to know Scala better. And to basically show that even if something doesn't yet exist in one of the libraries, that it's totally possible to build something relatively quickly with the right level of abstraction. And as a motivating example for that, I'm going to show linear regression using stochastic gradient descent implemented for both Scala collections and for Spark. How many people know about Spark here? Okay, quite a few. Those who don't, Spark is basically a modern alternative to Hadoop, which has a very functional API, very similar to Scala collections, so basically with all the standard combinators and essentially monads and whatnot. And it runs approximately 100 times faster than Hadoop for iterative programs, such as machine learning programs, for instance, and it has a much richer ecosystem, and the API is very functional. So essentially, if you implement an application for both Scala collections and for Spark, then your application should run on petabytes of data on thousands of nodes. So that is the beauty of that. So first of all, let me state the obvious. Machine learning is ubiquitous. You know, we see it in fraud detection to prevent your credit card from being compromised, in spam filtering, natural language processing for things such as topic modeling, to attach the topic label to a document to provide, for example, faceted search. There are recommender engines, such as the ones that Netflix is using. There's speech recognition everywhere in your car, even these days, right? There's question answering, and it doesn't have to just be Watson. There's Siri, of course. And you know, we're getting to the point of having self-driving cars. So really, machine learning is basically everywhere. It's not just a niche solution anymore. Okay, but to enable all of these machine learning solutions, we need a lot of models. There isn't a single machine learning algorithm that does everything, and for that reason, we have to basically have different implementations. And then, unfortunately, there are quite a lot of algorithms that a data scientist needs in a toolbox. So, you know, even just looking at regression itself, which means at models that take a bunch of either discrete or continuous inputs and produce a continuous output. So for example, trying to estimate the price of a house based on the square footage, the number of rooms, the distance from the highway, the school district, et cetera. The price is a continuous value, so for that reason, we would use a regression model. So many people know about linear regression, but there are tons of other algorithms. You can do regression using neural networks, using decision trees, random forests, et cetera. Then comes classification. So is it spam? Is it not spam, right? Just binary classification or multi-class classification, in which case we could probably just formulate it as a bunch of binary decisions. And here we again have tons of algorithms: logistic regression, naive Bayes, random forest, support vector machines, et cetera. There's also clustering. So basically, I could go on all day. There are hundreds of algorithms, and of course, the problem is that if you have so many needs to evaluate a bunch of business problems for potential automation using machine learning, you have to have all of these algorithms. So that is essentially the reason for the popularity of things such as R, which is a statistical language which has a bunch of implementations for these algorithms already. So if you look at R, for instance, they have approximately 5,000 statistical and machine learning packages already available. So if you need to build a random forest, there it is. Python also is becoming pretty popular in the machine learning community, not so much in the statistics community, but definitely in machine learning. Packages such as Theano and PyBrain are doing deep learning, which is essentially the hottest machine learning set of algorithms these days. There's matplotlib for plotting, there's scikit-learn for general purpose machine learning, SymPy for symbolic programming, etc., and LTK for natural language processing. And just to show you what my hope is to do in Scala is to basically have the same convenience that you can see here in this Python example, where in 30 lines of code, I can basically train the computer to recognize handwritten digits. And in fact, if you look at this code, you will realize that there are basically only 2 lines of code to train the algorithm, in this case, a support vector machine, and 2 lines to predict. The rest is just for printing the results on the screen. So this is the kind of convenience that you would expect in a language such as Python and R, given all the machine learning packages. So what is one to do if one is passionate about functional programming and high-quality code in a language that may have fewer libraries, potentially? But let's first focus on why I would even bother, saying that, oh, I don't really want to program in Python or R. Well, the first thing is probably a little bit controversial because, there are people who are passionate about Lisp or other languages which are functional but are dynamically typed, right? So I just want to say, with my first point, I don't want to start a religious war here. I just want to say that this is my personal preference for machine learning specifically. I would really like to have static typing. And the reason for this is that if you're running, for example, a Monte Carlo simulation that takes, 10 hours to execute, and suddenly you realize, oh, I have a typo in my code, like a literal typo, just a mistyped keyword or something, and the application blows up, then that's a problem because I wasted 10 hours running the application. And so basically, sure, you could write a lot of tests, but sometimes it's good for the compiler to help you. So that's just my personal preference. But from an objective point of view, there are other problems with these languages, such as R has a really terrible runtime. Everything is by copy. The memory consumption is crazy. It has a really bad garbage collector. Python has the GIL, right, the global interpreter lock. So your scalability is through multiprocessing, like it's, I don't know, web programming with CGI in 1994. So basically, it would be good to have better solutions. But since this is a functional programming conference, really the biggest problem for me personally is that it's imperative programming, right? Because there's no referential transparency. Everything is mutable. What the hell does I++ mean mathematically, right? In math, I basically have a function, submit a value, and I get a value back, right? So there's no one-to-one mapping between the math and the implementation. So frankly, the biggest problem for me is the functional aspect. And some people say R is a functional programming language, right? But it's not quite, because it's not optimized for functional programming. So here, for example, if you try to implement a sum on a list from scratch, sure, you could have a helper function inside a function, so it's a little bit more intelligent than Java, for example. But it doesn't have tail recursion, so even if I write a tail recursive algorithm, R will just blow up on me, so I cannot use it. Not a problem in Scala or in any language that was actually designed to be functional, right? Okay, so Python and R have these great libraries, but they're just bad environments for doing data science and actually for writing large programs, in my opinion. So what do we do? Hopefully we don't have to start from scratch. So what does the JVM offer, and specifically what does Scala offer? Because I would rather not write boilerplate Java with builder patterns and things like that. So there are numeric abstractions for Scala. There's Spire and Axel. Personally, I'm partial to Spire. It's part of the type level project along with Shapeless and Scala Z and other popular projects. It's a phenomenal project. Everything's based on category theory, really beautiful code. And in fact, they have a lot of optimizations. For example, they have this floating point filter that increases the accuracy of floating point calculations, so you don't have to use big decimal, for example, which is non-performant. So these guys are really, really smart. I don't even aspire to basically understand half of the things that they're doing. But it's definitely a very beautiful set of abstractions. Next comes linear algebra and optimization. You know, most of machine learning is at the end based on linear algebra, right? You're just multiplying vectors and matrices, or doing like matrix decomposition with SVD or something. So there are a bunch of JVM-based libraries such as ND4J and MTJ and EJML, but these are Java-based, so your syntax is pretty bad. You know, I don't want to write like dot multiply when I'm multiplying two matrices. Scala has operator overloading, which are just method calls essentially. So hopefully I can do better. Hopefully I can have type classes. Hopefully I have can have some principled programming. So there's Breeze. This is actually the first logo. It's a great library for linear algebra and for optimization. Python people also are really used to notebook-based programming. So they have the IPython notebook, which is a web-based system for plotting, evaluating code, and also storing the results. So you can see what code ran and how it was evaluated, and you can rerun it, but you already have the code paired with the results, so you don't have to recompute to view what was generated. So it's essentially like a modern version of Mathematica, right? Just brought to the web. So Scala actually has a lot of those too. There's Scala Notebook, which is essentially a port of the IPython notebook to work with Scala. There's the Spark Notebook, which embeds Spark in the Scala notebook. There's Apache Zeppelin and other projects. So there's no shortage of notebooks for Scala. There are a bunch of libraries for plotting too. There's the Lightning server, which actually is language agnostic, but they have a nice Scala binding. Then there's Wisp, which is the first logo, which is based on high charts. But you basically write Scala code. You don't have to write any JavaScript to do the plotting, which is pretty nice. And Breeze has some plotting also. And then when it comes to machine learning itself, Breeze already comes with some machine learning algorithms. There's deep learning for J for deep learning, although that's Java-based, so the syntax is, again, not particularly nice. But the library itself is good. And then there's MLlib, machine learning library for Spark, so that scales to big data level projects, to multi-terabyte or petabyte data sets. And then there's H2O, which also runs on Spark. These are all open source. I think the best part of the Scala ecosystem for machine learning is natural language processing. So since it's on the JVM, you can use the gold standards in terms of the best language parsers, such as the Stanford CoreNLP library. That one is Java-based, but there's Scala wrappers for it. But the two logos at the top, Epic and Puck, these are pure Scala implementations. For basically standard NLP problems, such as part of speech tagging and named entity recognition and so on. And in fact, PUC, this logo in the middle, that library even runs on the GPUs. So it really crunches through a lot of data very quickly. Okay, so what if there's no library for my particular use case, right? How difficult is it to build something? Well, in Java, I would probably have to write, tons of boilerplate just to insert the data from one list to another, even though they claim that, now there's more functional programming in Java 8, but that's not really functional programming except for, just taking lambdas into the basic combinators. But if you want to build something, if you have a good language, it really doesn't take that much effort. So that's what I'm going to show. The basic things apply here, right? You have first-class functions. So that's great, because if I have an optimized method, I can just insert the cost function and the gradient function into as arguments, and that's definitely elegant, right? And obviously In Scala, just like in any other functional programming language, you have monads, so you can create a whole pipeline of transformations. And Scala will actually let you get away with more stuff than, say, Haskell, right? Because it allows you to write Java-like code if you don't want to write functional code, but hopefully people switch to Scala for the reason that they want to improve their programming and become more functional. So then you obviously could make the code referentially transparent and immutable and declarative and use tail recursion and so on. Scala also has implicits, so you can basically generate one implementation and have implicit conversions so that if your code sees the type of a Scala list, then it's going to process that list, and if it instead sees a Spark RDD, the resilient distributed data set, then it'll just execute on the RDD. So with the implicits, you can basically provide a lot of backends without actually having to rewrite any of the machine learning code. And again, with type inference and named function arguments and so on, you don't have to write that kind of thing you would see in Java machine learning libraries where there's a huge builder pattern with a lot of mutable stuff going on. So in the next 15 minutes or probably less, I'm going to show you what could be done quite quickly from scratch. So I'm going to show two optimizers, stochastic gradient descent and AdaGrad, that will be using Breeze. So I'm going to reuse some of the libraries, at least to do linear algebra. And I'm going to implement linear regression and use implicit conversions to make sure that my implementation runs both on Scala collections, such as lists, sequences, vectors, etc., and it also runs on Spark for ultimate scalability on petabytes of data, on thousands of nodes. And just to quickly review linear regression, right? You basically have some value you want to predict, which is on the y-axis here, and then you have a thing that's correlated with it on the x-axis. But the correlation is imperfect, right? There are other dimensions of other features for the data that I would need to consider, but I don't have the data for, or basically the process itself is stochastic, so there's some randomness around it. But generally speaking, I can use X to predict Y, right? I can fit the best fitting line in it to capture the relationship, right? To minimize the sum of squared errors between the actual and predicted. So if you write a linear regression equation, it's basically Y is a function of all the x's, right? x1, x2, x2, xp for p dimensions, and each of these x's has an attached weight or a coefficient, and then it's just multiplying the featured by the coefficient and summing everything up. But since it's stochastic, it's not an exact equation, right? We have some error term, and we're trying to minimize this error. For optimization, these are gradient-based methods. So basically, I calculate the cost function. I figure out how the cost changes if I change each parameter. So I calculate the gradient, essentially a partial derivative with respect to that particular dimension, and then adjust the weight in the direction opposite to the gradient. AdaGrad is very similar. I don't want to go through the details because it's kind of complicated, but AdaGrad basically penalizes you for having large gradients in the past, which means this direction is just really unstable, so try not to adjust in that direction. Or you've seen a lot of examples in that direction because your data set is sparse and that dimension is very dense and other dimensions are sparse, so I'm going to boost the dimension that is less frequently seen because it's more significant. And then the cost function is basically the difference between actual and predicted squared. So if you write it in terms of linear algebra, it's just x beta minus y transpose times x beta minus y. But it's basically just taking the difference between actual and predicted and squaring that and summing up the results. So basically, let's just quickly look at some code here. So I think that the most interesting thing about this, especially considering the fact that Scala has implicit conversions, is this idea that you can provide multiple backends for your implementation. So you write a whole machine learning library, and then you just swap the backend using this trait and implicits, and basically you don't have to rewrite any of the algorithms to run on Spark, Hadoop, Scala collections, Apache Flink, which is a new framework inspired by Spark, and so on. or even like akka streams or something. So basically, the trait just has a bunch of standard features that, for example, any functional collection would have, like map, reduce left, flat map, etc. And the only thing to remember if you want to distribute your processing is that it's also important to have an aggregate method. And aggregate basically is the same as a fold, but the sequential op here, the sequential operation is essentially what a fold is, but the combo op takes two folds from two nodes on the cluster and then aggregates the results from two nodes, right? Because it's essentially Spark is a MapReduce framework still. So you're doing some sequential processing on each node, but then you have to collect the results from each node to aggregate them at the end. So it's like a extended version of a fold. And once we have this trait, we can basically implement it. And there's a case class here for traversable, which is one of the traits in Scala collections. And basically, in this case, we can just delegate directly to the Scala collections because they have these implementations. And we do the same thing for the RDD, the Spark Resilient Distributed Dataset, which is a distributed big data version of a collection, essentially. And once we have that, all we have to do is just have these implicits here, which if they're in your context, if they're imported, then they can take the traversable, the Scala collection, and if your code expects this dist data representation, then it's going to do the conversion automatically. And the same thing will happen for an RDD for Spark. So that basically makes any code you run against this dist data trait run on both Spark and Scala collections. So it's really simple, but it's actually very powerful. And then we have some, essentially beans, just containers that will contain your target value, which is the thing you want to predict, and features, so the things that explain the variation in the thing you're trying to predict. And some other sort of boilerplatey things, such as the optimization history. You want to know what the value was for the cost at each iteration of your algorithm, and what the weights were, and the gradients, and so on. So these are probably the less interesting parts here, but just wanted to mention them because that's necessary to explain the rest. But the key thing is the optimizer here, right? So the optimizer method has to get all the parameters from the user, such as how many iterations to run this algorithm for, and the random number generator seed in case you want reproducibility, and the initial learning rate for the algorithm, and the gradient function, and the cost function, and the update function, which is actually the specific optimizer you might be using, and the mini batch fraction, which essentially means that you're not processing your whole data set all at once, but you're instead sampling and processing on just a few observations at a time. This is the scalable thing to do, and it also converges faster. And this is actually really trivial. You're basically just initializing the weights and the gradients with some random numbers because you don't have any history. And then you're just folding, right? I have some number of iterations, and when I'm folding, I get this accumulator, which is the previous history value, right, for the cost and the gradient and so on. And then if it's not the last iteration, then I'm basically calling this update function, which is my optimizer, and passing the gradient function, cost function, and the last value of the history to get the new value, right? So it's very standard functional programming here. But we need to implement the optimizers. So the implementations are actually quite simple. In this object, which is reusable across all optimizers, all I'm doing is just sampling some data, and then calling the cost function, which is specific not to the optimizer, but to the machine learning model, such as linear regression, logistic regression, neural network, et cetera. And just storing that. And then the algorithm itself, as you may remember from the slides, is just taking the learning rate and dividing it by the square root of the sample size times the iteration number. That's the change in the weight, in the learning rate of the stochastic gradient descent. And then we're just taking the weights and subtracting the gradients times this new learning rate. So, and because I'm using Breeze here, I can actually use this symbolic notation. So these are element-wise differences and element-wise multiplication. In this case, eta is just a scalar, but there's also element-wise multiplication for vectors. So Breeze is helping me here because I don't at least have to think about the linear algebra details. Basically, this is really the key. I need some little effort for sampling because I may want to have sampling with replacement or without replacement, right? With replacement is really trivial. I just toss the coin, a particular number of times, and the random number generator is generating a value within a particular range, and it can generate duplicates. So sampling with a replacement is trivial, but if you want without replacement, then you can do something like this, right? You can say, I have an index sequence, which is the sequence from which I'm sampling, and I have the size, so the number of elements I'm drawing from it, and then I have the accumulator, and basically, until I get the number of elements I want, I'm just calling myself recursively, and the index sequence from which I'm sampling is shrinking, and I'm moving the elements to the accumulator, so what I'm sampling from will not have the things that are already sampled. So, standard functional programming, not particularly interesting, but it shows the power of using functional programming to do math, right? That it's more obvious than doing imperative programming. Anyway, so basically right now with this implementation we have, and we also need to just briefly cover the cost function here. One moment. Yeah, so we have the cost function for the linear regression. It's just basically the sum of squared differences between actual and predicted. So that's the features, which are basically the values for the example times the weights minus the target, and then I'm just mapping and squaring, and so map reduce, right? Very simple. So again, the power of functional programming, not writing for loops or something. And the gradient is also pretty simple. This is straight from linear algebra, so I basically took the mathematical formula and I just wrote it down. So this is all, believe it or not, this is very little code, and this linear regression implementation will not just run on Scala collections, but if you have, hundreds of terabytes of data and you have tens of nodes, this can run on Spark. So let me just briefly demo this. I generated a data set where I have 1,000 observations of random numbers for x for the explanatory variable or for the feature, and then y is equal to 3, which is the intercept, plus 10 times the random number x for that particular example, plus some random disturbance, which is another Gaussian value. So basically what I expect is that the estimated coefficients are 3 and 10, because that's how I generated my data set. And as you can see here, this Adagrad optimizer seems really unstable at the beginning, whereas stochastic gradient descent seems stable. But if I actually zoom in towards the end, and this is the WISP library for Scala for plotting, which uses high charts internally, then you will see that the stochastic gradient descent didn't converge as well. The cost is actually higher, the error rate is higher. So in fact, if we look at this, right, we expected the intercept to be 3 and the slope to be 10. and stochastic gradient descent estimated 3.4 and 9.2, whereas AdaGrad estimated 3 and 10. So AdaGrad had much bigger errors at the beginning, and then it actually converged to a better value at the end. So, everything with machine learning has to do with basically, empirical evaluation. There may be theories about how these algorithms behave, but nothing replaces actually seeing it. So plotting is actually really important. So what I showed here is that, the ecosystem isn't completely non-existent, that libraries exist for natural language processing, machine learning, et cetera, but also if you want to build something really quickly, you can reuse these components. Like I wouldn't want to write my own plotting library. I wouldn't want to write my own linear algebra library, but I want to have the linear regression work on Spark, for example. So then, just connect the components, benefit from the functional constructs, not to write too much boilerplate, and it's actually not that hard. And so I guess that's essentially it. I hope I haven't gone over time. But if anyone has any questions, I would love to answer them. No questions? Sure, that is a very good question, because I was actually really lucky. I used to be that MATLAB data scientist 5 years ago, and I had the great pleasure of working with a real software architect who basically inspired me. I think a mentorship has a lot to do with it. People are smart and they're probably interested in doing things better. It's just that they have to be nurtured to do so. If you're getting a whole team of Haskell programmers and you expect the data scientist to pick it up right away, maybe they will not pick it up the next day. But if there's actual mentorship, I'm pretty sure they'll be as passionate about that as I am, because obviously functional programming has a better mapping to math than does imperative programming or unprincipled programming in general, right? So it's totally possible. I've been observing a data scientist that I used to work with in the previous company. She's now at a new company, and I don't think she was prohibited from using R per se, or Python, because, for example, Spark has a PySpark API, so you can use Python instead. But the company really wanted the code base to be more legible and to have type checking and to have all the functional constructs and so on. So they made a point to ask her to get up to speed, and she found it interesting. And I saw her at the Spark Summit a few days ago, and basically she said, I may not be a Scala expert, I may not know how to write Scala macros, I may not know about, I don't know, a monad is a monoid in the category of endofunctors type of thing, but she was definitely really interested in getting better at development in general, not just using a better language. And so I think it's a matter of inspiration, essentially. And of course, people will whine a little bit that, hey, I don't have 1,000 libraries like for data science, that sometimes I have to build something, but they'll actually realize, oh, it scales, and I don't have to use multiprocessing to scale, and I will not run into a bug later on because this type system helps me, or because the constructs are better in just the functional programming constructs themselves. So yes, data scientists who actually do functional programming are rather rare, but I really found it's a matter of inspiration, not the lack of interest. They just don't know what they're missing. If you show it to them, they'll really never look back. That's just my observation. Thank you.